Hello, my name is Tomas Skopal. I'm from Charles University and I will present a work called Similarity versus Relevance from simple searches to complex discovery. This is a joint work with my colleagues from the same university. When using similarity search, we are mostly facing the basic problem of query by example and KNN query. So we are using some similarity function. I will call it direct similarity. And the scenario for the search is that we are using an example for a query and we are realizing the KNN search, the search for K nearest neighbors. And I will now illustrate the basic paradox of this model. So let's have a query, the dog here, the image of a dog, this is the example, and we are now searching for the most similar dogs in a dataset. And we get some ranked result from the most to least similar. So we get something like this. And this is golden retriever. So we get on the first place another golden retriever. Here another golden retriever. Here there is one golden retriever and some Labradors. And here this is Labrador. So this is less relevant or less similar to this original query. So this is what we get. But do you see the paradox? Actually, we are searching for something that is as close as the query as possible, but actually that's the query itself. So the best result we already have before we start the query. That's the query example. Of course, this is not so simple because we are using KNN search and the query by example, and we find it useful. But this usefulness is not because of the basic similarity model, but because of some external data that we get together with the results. So for example, this image of retriever was connected with the Wikipedia page and we get some information, and that's why the query result is useful, because the query was actually the perfect result. So we actually face the problem of this paradox. And in turn, this reflects in somehow limited expressive power of the simple search, the query by example paradigm, and the KNN search. So also the effectiveness of the retrieval is somehow limited by this paradox. Now, what to do with that? Of course, we would like to have some better and more rich capability of querying using examples. But we would like to extend the notion of relevance from simple or direct similarities to something more general and more useful for our applications, for our tasks. So the baseline we already have and we all know is the direct similarity. So this is the query and we get the results somehow ranked. This is what we already saw in the previous slide. And we are mostly using this kind of search for rather simple retrieval problems because we target the intent of our search with the query, and we are mostly interested in narrow search and we focus on precision. So the more precise the result with respect to the similarity of the object, the better. But we would like to also have another concept of relevance that is not just direct similarity. We would like to capture other concepts that somehow contribute to relevance of data to a query, but it is not direct similarity anymore. It could be various kinds of complementarity of the individual results, orthogonality of results, and in turn some transitive similarity or relevance that exhibits some kind of transitivity. And this kind of retrieval is more suitable for complex retrieval tasks, not just really fast direct searches like this, but more complex scenarios like discovery or exploration of data. And we also focus not just the precision, but also the recall. And the recall in some scenarios is really important. So we widen the search. So how to imagine this extended concept of relevance beyond the direct similarity. So let's start with the same example. We still have the same golden retriever dog, and we could search, of course, something that is really close to the direct result. So we get some golden retriever dog results, but we would like to generalize more the query, and we could get far from the original example. So for example, we would like to also retrieve more complete result. That's why we are targeting the complementarity. And these are just dogs. They're still similar to the original, but not so much. But they are still the same relevant, maybe. So this is the difference. This is less similar to this, but maybe the same relevant as this. And we can get even more far. So here we get pets, and they are not dogs at all. So there is a cat, there is a mouse, there is a parrot, and there is even a spider. Spider is completely not similar to dog, but they could be sharing the same category, and that's the category of pet. So by this illustration, we could motivate our intention to widen the concept of relevance to something more than just direct similarity. From the other hand, for example, we can start again with the dog, and we would like to get completely different concept that is not similar to the original query anymore, but is still highly relevant to the query anyways. So let's start with the dog, and we can get, for example, a rescue dog. Why? Okay, that's a dog, but that's the rescue dog. But from the rescue dog, we can maybe get even more far from the original query, and we can get something that is completely not similar to a dog. But using some kind of transitivity, we can get to different objects that are transitively relevant to the original object, to the dog. But here it's rescue. It could be a person, it could be a helicopter with a person, and so on. So this is something more than direct similarity, and we would like to address this problem because it's quite limiting the applicability of similarity search as an area just to quite very simple problems. Of course, all of these results could be retrieved somehow, even today, with some tools. We have different options how to increase the expressive power of search that goes beyond the direct similarity search. The first, what we can use is early fusion techniques. So to combine multiple descriptors of objects to implement some multimodal or even multimodal search. We could use multiple example queries, and we can also use late fusion techniques like re-ranking, top K, aggregation of result. There are other alternative ways how to use different ways of getting a result to a simple query. We can also put the human in the loop, make the process of retrieval interactive, and employ knowledge gathered by user feedback, the exploration process that is interactive, and using the various kinds of browsing techniques. Okay, this is already on the scene. We can use it in different softwares, in different models, but all of these ways how to increase expressive power is that they always include an extension to the basic query by example concept. This is not simple query by example anymore. In simple query by example, we have similarity function, query, and data set, and that's it. And maybe K, the number of nearest neighbors we need. In this applications, on these extensions, we need more complex retrieval model that includes other parameters, other user parameters, also other models for interaction, model for presentation, the fusion models, and so on. So we cannot reuse some general query by example engines for these extended search applications. And what we are now presenting is something that still fits the query by example concept because it's still a similarity function. And this similarity function we call data-transitive similarity, and basically it is just a variant of non-metric similarity function. The difference between other functions is that this similarity function is dependent on the data set. So this similarity function is dependent on data we actually have in the data set. So it's not a priori designed similarity applied on arbitrary data set. We already have the data set, and the similarity works with the data set. And it's a meta model. So it's not some very hardwired similarity function. It's a meta model that works with the ground distance. Many other functions work with ground distance also here. And using this meta model, we actually try to aggregate the similarity of two objects that form a chain. The first object is the start of the chain. The second object is the tail or end of the chain, and there are some n other objects in the chain. So the formula for the meta model is this. So we have the object 1, object 2, as usual, when we are measuring similarity, but we have other n objects here that are from the database D, and we are trying to compute some overall similarity between x and y using some intermediate objects I1, I2, and so on that form a chain. For this, we are using inner aggregation, denoted like that evaluates the overall similarity between x and y using the consecutive aggregations with the intermediate objects. And finally, we are picking the value or that chain that exhibits the best score with respect to some outer aggregation. It again could be any aggregation function. This and this could be any aggregation function. For example, here there are some examples for this inner aggregation. It could be just a sum or minimum, maximum, product, or subtraction of product. So it could be anything. And we get just a simple value, the same way as we get a value from any other similarity function. What is different from the approaches that use any kind of extension from the query by example is that it actually still is usable in standard query by example searches, because it's just a similarity function. It does not introduce any extension on top of similarity. There is nothing external. So we can plug this similarity function into any existing search engine that provides KNN searches. It could be also indexable. Of course, this is much more complex to evaluate, because this will be more expensive to evaluate, because it must work with the data from the data set. But again, this is a matter of implementation. It could vary from very cheap implementation, maybe in the complexity of OD, to something that is quite expensive. Some power of the size of the data set D. How did we find out this could be useful for anything? Well, this data-transitive similarity is inspired heavily by the join operation in relational databases, because in relational databases, the join operation is the mostly used operation ever, and it provides some result to a query. And the results, of course, must be somehow relevant to the query. So the joining of elements from a database by means of join operations actually does similar process as we are using here in the form of aggregating the chains of objects. So we join objects together and we get some overall result that is still relevant to the original query. Of course, the difference here is that we need to put the complex behavior of the joining into just regular similarity function. So we have hidden everything inside the computation of the similarity function. So the semantics of the similarity is, of course, within the similarity function, and it is bound to the data set. That's why it's called data-transitive similarity. And of course, the data set is just a parameter of the function, but a huge parameter, of course. That's the huge, that's the whole database. What allows us, or what semantics are favorable to model using this data-transitive similarity? It allows us to, for example, almost eliminate duplicate results by properly setting the inner aggregation function. And so by this way, we could preserve the diversity of results. This is something that could behave similarly as our previous work, that's more than 10 years ago, where we introduced the concept of distinct KNN queries. And the motivation was we could get, using normal KNN query, a result like this. This is a query object, a photograph of sun, and we get almost the same results as actually is the query. Here we again return back to the paradox of KNN query. We get the best possible result. This is really similar. Everything is really similar to the query, but it's completely useless. Who wants to retrieve just duplicates? That's why we introduced back then the distinct KNN queries, and we were able to retrieve results that are not the same, like here, but are very diverse. They're different. They differ from each other, but they are still somehow similar to the original query. You can see that. And this is just one example what could be done using the data-transitive similarity without introduction of some other concept like the DKNN concept was the 11 or 12 years ago. And generally, we can use the data-transitivity for modeling other concepts of relevancy between query and data that are generally orthogonal and complementary to the query example. Now to the application. We didn't apply this concept of data-transitive similarity to the traditional domain, which is multimedia, which is nice to present, and it's really popular and everybody understands that. Because in multimedia domain, the direct similarity actually works quite well, because in similarity, in audiovisual similarity, we are satisfied even with direct similar results. But there are other domains where the direct similarity fails at all. So there is no meaning to use direct similarity. For example, there is a domain of open datasets. Open datasets are datasets published by governments and other public bodies on the internet, and they must publish by the law information about municipalities, and actually there could be anything published. And these datasets are really hard to search because they have very bad description. And the models based on direct similarity used for searching datasets are not applicable because they return very trivial results or does not return any results at all. And the reason is that there is very sparse metadata associated with the common datasets. Like here, there is example, we have metadata of textual form. There is a title of the dataset. The dataset is called floods in the 19th century. There are some keywords to the dataset. There are 3 keywords: floods, environment, GIS, and there is some description, which is this one sentence. And based on this, the user is supposed to search datasets in so-called dataset catalogs, which are mostly web applications that serve as as an interface for searching datasets, for open datasets. One of them is, for example, the Czech National Open Data Catalog, foundable on this URL, and you can search for datasets using just keywords. So just keyword search is provided in these catalogs. It's not just this Czech catalog. There is also EU catalog of datasets, and it's very similar. One could say, okay, why to use this sparse metadata? You could use the content itself, just the datasets. So you look inside the datasets, and there is a huge amount of data. But there is a problem with the content, because the datasets are generally not complying any standard. There is a very wild jungle of representations of the dataset. It could be CSV files, PDFs, spreadsheets, various dumps from databases, geographical information like maps, anything stored in JSON or XML, and there is no database schema attached to this. So there is no metadata on top of the structure of the dataset. So everything we have actually is this metadata that is associated with the dataset. Now search for dataset with this sparse information. So we try to use the data-transitive distance for the hard problem of dataset discovery, where we actually used the meta-model formula, and we replace the particular components with some particular functions. So, for example, the outer aggregation was used as the minimum, the inner aggregation was used maximum. We just used only one intermediary, so there is just one intermediate object between x and y, so there are always triplets in the chain that we are evaluating here. And the ground distance was chosen the classical cosine distance, and the descriptors that we are using for the objects themselves, for the datasets, are just vectors created from the concatenated information, title, keywords, and description by means of TF-IDF, and we are using the back of words model. Well, so this is the basics setting, and now we can observe how it works with the dataset transitive distance compared to classical direct distance, that is again the cosine distance that is usually used for measuring the similarity of text, which is our case because we have the metadata in form of text. And now let's analyze the dataset. We used the dataset from the National Open Data Catalog and computed the distance distribution by both the distance cosine distance and the data-transitive distance, data-transitive similarity. And we got two distributions. You can see the red one, the red curve, is the distribution of the cosine distance. And we can see that the data sets are likely to be very dissimilar, not similar. Because the small distances, there is very few distances that are small, and most of the distances are very large, and the majority of distances is maybe maximal. This is normalized to 1, so there is very many of maximal distances here. But there is something in between. If we use the data-transitive similarity, that is configured like this, so we are using the cosine distance as a ground distance, then we get another distribution, which is the green curve, which starts at 0.6 because we intentionally filtered everything that is below 0.6 because it was evaluated as near duplicate. That was the problem of having duplicates, and everything else is in this distribution. And we can identify two peaks in this distribution. One peak is for smaller distances, and one peak is for higher distances. So these distances should stand for relevant data sets. So we have the distances are just distances between two data sets. So these distances have small distances. These data sets have small distances, so these are more relevant, and these are less relevant or non-relevant. So we have quite nicely separated two categories of data sets: non-relevant, relevant. Then we used some evaluation where we employed 5 human evaluators that should rank or score a result to a particular query by evaluating a set of triplets of data sets. So every human evaluator got a set of triplets like this, where the first member is the query dataset. That's the query example, but in form of dataset, not image, but dataset. Then there was a result dataset that was actually the result, that was the answer to the query. And there was the one intermediary dataset that served as the actor that realized the transitivity in this distance. Remember, the data transitive distance is defined like this, and there was one object, here it would be I1, that is in the middle between x and y. So there was just one intermediary object. And every evaluator should evaluate or score the result to the query with respect to the intermediate object as relevant or not relevant. So every data set got score by every evaluator. So every triplet we have here could get 0 to 5 points, because we have 5 human evaluators. Everyone might assign 0 or 1 score to the result as relevant or not relevant, and we can observe how the results look like in some aggregation. So what we can observe on the left is that at first this method of evaluation was quite consistent, because 78% of the scores of all the evaluators were in agreement. So 78% of scores either score a dataset or result as non-relevant or relevant. So these scores, 5 means the triplet got 5 ones, so it's totally relevant result. This result to the query is totally relevant. That's for 5. Or the result was completely irrelevant and got 0. And there also was 1 and 4, which is mostly relevant or mostly non-relevant. So 78% of these scores were distributed among all of these triplets. So it was highly consistent. Also, 57% of all of the triplets were ranked as relevant. And here we must realize, or we must emphasize, that these triplets were only composed of results that were not achievable by the standard direct similarity. So everything the evaluators got was not findable by the cosine distance, because 66% of the datasets were not reachable by direct similarity, because the distance of the cosine distance was maximal. So as it's actually this number, 66% dataset, is actually this case. This is the maximal distance, 1, and this is very high portion of similarities in the direct distance, cosine distance is maximal. So everything we can see here is extra information that the data-transitive similarity brought on top of results that could be ever achievable by that cosine distance. So from this point of view, it's quite nice result that we got some number of data sets that were relevant to a query. In the second figure, we can see the distribution of scores related to the data-transitive distances. And here we can see clearly that the higher the distance, the data-transitive distance, the smaller the similarity, of course, the smaller number of scores. So distances that are over 0.8 are also highly or frequently ranked as 0 relevant, so non-relevant. And on the other hand, data set exhibiting lower data-transitive distances, so they should be similar because this small distance is similarity, were also ranked as highly relevant. So here the design of the data-transitive distance follows the thesis of the similarity search as the concept of searching for relevant data. We indeed found relevant data using small similarity, in this case data-transitive similarity. So this was quite brief evaluation of the whole concept, and we can provide also the qualitative analysis, and we can just see two examples of these triplets. Here is a triplet of dataset 1, which is the query, it's Q, then the result dataset is actually the result, and the intermediary dataset, which is this I. And we can see their metadata, we can just watch them as users, and we can see that the first dataset talks about floods in 19th century. It has keywords floods, environment, GIS, and that's the description. And then we can see the result dataset that basically has no keyword in common with the query dataset. You can see that there is flood in century, there is water reservoirs, management, river basins, forests. The keywords here are floods, environment, GIS, here water tanks, water management, there is nothing in common. And there is quite large description, but still, this was ranked as relevant to the query thanks to the intermediary dataset that basically connects the two with some overlap. Here we have GIS and floods and environment, and here we have water here, and we have water here, and there are maybe some other, I don't see them right now. So actually this intermediary dataset acts as a connector in joining two datasets together, Q and R, and this is why we were talking about the joins in databases, because it actually does the same job here. So this is the first example. Another example is with these three datasets, again, query, intermediary dataset, and result, and it's about housing. So the query is a dataset about housing, young, sociology, housing research, housing young, housing, and Brno city. And the description, and there is quite long description, that's not all of it, there are 3 more paragraphs of text, so it's very large description, but here, for example, it's very small description, just this, and this result is just this. But again, we can see these two have nothing in common much, but thanks to the intermediary data set, we can find overlaps between these two and these two as well. So we get result for this query. And we couldn't get this result without the dependence of the similarity on the data, because this intermediary data set is in the database. So we cannot just model a similarity that would relate this query data set to this result data set. Otherwise, then we should have some external knowledge base for this. And instead of external knowledge base, we have the data set itself, or the database itself, and it includes this intermediary object that serves as the connector between the query and the result. So, to conclude, we have introduced the data-transitive model of similarity. It's a meta-model. It serves, or it aims at extending the relevance that is usually interpreted as the direct similarity to something more general, to more general concepts. The means how to achieve it, this is the transitivity, and we can get results that are more complete, more orthogonal, or more complementary to the original query. We still have the similarity model defined as a similarity, so we can use any non-metric query by example engine and just to plug it into this engine. We do not need anything special for using this kind of similarity. It's just a similarity function. And we have find out, or we have shown, that this extended definition of similarity and or relevance is especially applicable in hard problems hard retrieval problems where we have sparse descriptors that almost carry no information or very little information, and that is not achievable by the direct similarity. So direct similarity fails in these cases. And this was the case of the open data set, but not usual. The multimedia retrieval is not the usual case, so that's why we use the open data set. Okay, so that was all from me. Thank you for attention, and I'm waiting for your queries. Thanks.